Welcome, fellow space enthusiasts, to an extraordinary journey through our solar system. Today, we're embarking on an exploration that will challenge our traditional definitions and expand our cosmic horizons. Nestled between the red plains of Mars and the swirling storms of Jupiter lies a celestial object that defies easy categorization. It's not quite a planet, yet it's far more than just another asteroid. This enigmatic world is none other than Ceres, the dwarf planet that's rewriting our understanding of solar system formation. As we dive into the mysteries of Ceres, prepare to have your preconceptions shattered. This small yet mighty world is a testament to the incredible diversity of our cosmic neighborhood. Its unique position in the asteroid belt makes it a key player in unraveling the secrets of our solar system's early days. But Ceres is more than just a relic of the past. Recent discoveries have shown that this dwarf planet is a dynamic, evolving world with active geology and potentially even ongoing chemical processes. As we explore Ceres together, we'll see how this tiny world is forcing astronomers to rethink their theories about planetary formation and evolution. So buckle up and get ready for a mind-bending adventure that will take us to the very edge of our current scientific understanding. Ceres may be small in size, but its importance in reshaping our cosmic perspective is nothing short of revolutionary. Imagine a world with hidden oceans beneath its icy crust, where cryovolcanoes erupt plumes of ice and salt into the void of space, and where the building blocks of life might be brewing in dark, subterranean chambers. No, I'm not talking about Jupiter's moon Europa or Saturn's Enceladus. I'm referring to a world much closer to home, one you've probably never imagined could be so fascinating. Ceres, once dismissed as just another unremarkable asteroid, harbors secrets that could completely transform our understanding of habitability in the solar system. This diminutive world, barely the size of Texas, has been hiding in plain sight, its true nature masked by its unassuming appearance. But appearances can be deceiving. Recent explorations have revealed that Ceres is a complex, geologically active world that challenges everything we thought we knew about dwarf planets. Its surface, dotted with mysterious bright spots, hints at a subsurface ocean that could potentially harbor the conditions necessary for life as we know it. As we delve deeper into the secrets of Ceres, prepare for revelations that will shake your certainties about what's possible beyond Earth. This little world is proof that in space exploration, size doesn't always matter. Sometimes, the most groundbreaking discoveries come in small packages. Get ready to have your mind blown as we uncover the extraordinary features of Ceres, a world that's forcing us to redefine our understanding of planetary science and expand our search for potentially habitable environments in our cosmic backyard. If this introduction to Ceres has piqued your curiosity and left you hungry for more cosmic discoveries, don't forget to hit that like button, and make sure you're subscribed to Exploring the Universe for more mind-bending journeys through space. Together, we'll continue to unravel the mysteries of our solar system, one fascinating world at a time. The universe is full of surprises, and you won't want to miss a single one. On January 1, 1801, the night sky revealed a secret that would change our understanding of the solar system. Italian astronomer Giuseppe Piazzi, while working at the Palermo Astronomical Observatory, spotted a faint point of light that didn't behave like the other stars. Little did he know that this discovery would lead to over 2 centuries of scientific debate and reclassification. Piazzi initially thought he had found a comet, but as he tracked the object's movement over the following nights, he realized it was moving too slowly for a comet. He had, in fact, discovered the first and largest object in what we now know as the asteroid belt. The scientific community was thrilled. At the time, astronomers were searching for a missing planet that they believed should exist between Mars and Jupiter, based on a mathematical rule known as the Titius-Bode law. Ceres seemed to fit the bill perfectly, and it was hailed as the 8th planet of our solar system. However, as more objects were discovered in similar orbits, astronomers began to question Ceres' planetary status. By the mid-19th century, Ceres was reclassified as an asteroid, the first of many in the newly recognized asteroid belt. The story doesn't end there, though. In 2006, the same year that saw Pluto's demotion, Ceres received a promotion. The International Astronomical Union created a new category, dwarf planets, and Ceres, with its nearly spherical shape and substantial size, fit the criteria perfectly. The name, Ceres, itself has a fascinating origin. It comes from the Roman goddess of agriculture, grain crops, fertility, and motherly relationships. This name was proposed by the German astronomer Johann Elert Bode, keeping with the tradition of naming celestial bodies after mythological figures. The choice proved to be surprisingly apt, as we would later discover Ceres' potential connection to organic compounds and possible subsurface water, elements crucial for agriculture and fertility. Ceres may be small by planetary standards, but it's a giant in its own domain. With a diameter of approximately 940 kilometers, 584 miles, it's by far the largest object in the asteroid belt, accounting for about a third of the belt's total mass. To put its size into perspective, if Ceres were placed on Earth, it would stretch from New York City to Chicago. One of the most intriguing aspects of Ceres is its shape. Unlike smaller asteroids which can have irregular, potato-like shapes, Ceres is nearly spherical. This is due to its own gravity, which is strong enough to pull the dwarf planet into hydrostatic equilibrium. This spherical shape is one of the key factors that elevated Ceres from asteroid to dwarf planet status. The composition of Ceres is equally fascinating. It's not just a giant rock hurtling through space. Instead, it's a complex mixture of rock and ice. Scientists estimate that up to 25% of Ceres' mass could be water, primarily in the form of ice. This high water content is crucial to understanding Ceres' internal structure and potential for geological activity. Ceres' surface is dark, reflecting only about 10% of the sunlight that hits it. This is due to its composition, which includes clay and carbonaceous materials. However, this dark surface is punctuated by numerous bright spots, which have been found to be deposits of salt compounds, hinting at a complex geological history. The internal structure of Ceres is thought to be differentiated, meaning it has layers of different compositions. Current models suggest a rocky core, surrounded by a mantle rich in water ice, and a thin, dusty outer crust. This structure, particularly the potential for liquid water beneath the surface, makes Ceres an exciting target in the search for potentially habitable environments in our solar system. Despite its small size, Ceres continues to surprise scientists with its complexity. From its nearly round shape to its intriguing composition, this dwarf planet serves as a unique laboratory for studying the early solar system and the potential for life beyond Earth. The Dawn mission, launched by NASA in 2007, marked a significant milestone in space exploration. It was the first spacecraft to orbit two distinct celestial bodies beyond the Moon, showcasing the potential of ion propulsion technology and opening new frontiers in our understanding of the early solar system. Dawn's journey was ambitious and complex. After launching from Earth, it first set its sights on Vesta, the second largest object in the asteroid belt. Arriving at Vesta in 2011, Dawn spent 14 months studying this protoplanet, providing unprecedented insights into its structure and history. But Dawn's mission was far from over. After bidding farewell to Vesta in 2012, the spacecraft embarked on a 3-year journey to reach its final destination, Ceres. On March 6, 2015, Dawn made history as it slipped into orbit around Ceres, becoming the first spacecraft to orbit a dwarf planet. NASA's New Horizons would fly by Pluto a few months later, but wouldn't orbit it. The revelations from Dawn's mission to Ceres were nothing short of revolutionary. As the spacecraft spiraled closer to Ceres' surface over the course of several months, it unveiled a world far more complex and intriguing than scientists had anticipated. Some of the most surprising discoveries included the presence of organic compounds on Ceres' surface, suggesting complex chemical processes, evidence of recent geological activity, including cryovolcanism, the discovery of a 4-mile-high solitary mountain, Ahuna Mons, believed to be a cryovolcano, the detection of a thin, transient atmosphere of water vapor, signs of subsurface liquid water, raising questions about Ceres' potential habitability. These findings fundamentally changed our understanding of Ceres. Far from being a static, rocky body, Dawn revealed Ceres to be a dynamic world with ongoing geological processes and a complex internal structure. The Dawn mission officially concluded on November 1, 2018, when the spacecraft ran out of fuel. However, the wealth of data it provided continues to fuel scientific research and reshape our understanding of dwarf planets and the early solar system. One of the most captivating discoveries of the Dawn mission was the presence of numerous bright spots on Ceres' otherwise dark surface. As Dawn approached Ceres, these spots became a source of intense speculation and excitement among both scientists and the public. The most prominent of these spots, located in the 57-mile-wide Achater crater, was visible even from Dawn's early, distant observations. As the spacecraft got closer, it became clear that this wasn't a single spot, but a complex of highly reflective areas. In total, Dawn identified more than 130 bright spots across Ceres' surface, varying in size and brightness. The largest and most reflective of these is an Achater crater, now named Cerealia Facula, which is accompanied by a group of smaller bright areas called Venalia Faculae. After much analysis, Scientists determined that these bright spots are primarily composed of sodium carbonate, a type of salt. Some spots also contain ammonium chloride. This was a surprising discovery, as these compounds aren't what scientists expected to find on a body in the asteroid belt. The presence of these salts has profound implications for Ceres' geological history and current state. These salts are typically formed in the presence of water. Their existence on Ceres' surface suggests that salty water once existed on or near the surface. The brightness of the deposits suggests they are relatively young. If they were old, they would have darkened due to space weathering. This implies recent or ongoing geological activity on Ceres. The composition and distribution of the bright spots provide strong evidence for a subsurface layer of briny liquid. The leading theory is that impacts exposed this brine, which then sublimated, leaving behind salt deposits. Some of the bright spots, particularly those in a crater, may be the result of cryovolcanic activity, where salty water erupts from beneath the surface and freezes. These bright spots have thus become key evidence in the case for liquid water beneath Ceres' surface. The possibility of a subsurface ocean or brine reservoirs has elevated Ceres' status as a potential harbor for simple forms of life, making it a prime target for future exploration missions. The story of Ceres' bright spots demonstrates how a seemingly simple observation can lead to profound insights about a distant world, reshaping our understanding of the diversity and complexity of bodies in our solar system. Rising majestically from the otherwise relatively flat surface of Ceres stands Ahuna Mons, a mountain that has captivated scientists since its discovery by the Dawn mission. This solitary peak, reaching a staggering height of about 4 kilometers, 2.5 miles, is not just any mountain. It's believed to be a cryovolcano, or ice volcano, a feature that has reshaped our understanding of Ceres' geological activity. Ahuna Mons is truly a sight to behold. Its steep slopes and domed summit give it a distinctive appearance, quite unlike any mountain on Earth. The mountain sides are streaked with bright material, similar to the mysterious bright spots found elsewhere on Ceres, hinting at its unique composition and formation process. The evidence for Ahuna Mons being a cryovolcano is compelling. Its dome-like shape is consistent with volcanic features formed by viscous materials. Spectral analysis suggests the presence of salts and other materials consistent with cryovolcanic processes. The absence of an impact crater suggests an internal formation process rather than an external impact. Ahuna Mons appears to be relatively young, potentially less than 200 million years old, indicating recent geological activity. The concept of a cryovolcano might seem alien, but it's a process where water, ammonia, or methane erupt instead of molten rock. On Ceres, this likely involves a mixture of water, salts, and mud. The existence of Ahuna Mons has profound implications for our understanding of Ceres' internal processes. It suggests that Ceres has, or at least had in the recent geological past, a source of internal heat. This heat, combined with the presence of subsurface volatiles like water, drives cryovolcanic activity. Moreover, Ahuna Mons isn't alone. Recent studies have identified other potential cryovolcanic features on Ceres, suggesting that such activity might be more widespread than initially thought. This paints a picture of Ceres as a geologically active world, constantly reshaping its surface through processes we're only beginning to understand. One of the most exciting possibilities raised by Dawn's observations of Ceres is the potential existence of a subsurface ocean or regional reservoirs of liquid water beneath its icy crust. This hypothesis has transformed our view of Ceres from a static, rocky body to a potentially dynamic, water-rich world. Several lines of evidence support the existence of subsurface liquid water on Ceres. Dawn's gravity data suggests a lower density outer layer, consistent with the presence of water. Features like Ahuna Mons and the bright spots in a crater suggest the upwelling of water-rich material from below. The presence of hydrated minerals and salts on the surface indicates past or present water activity. Certain surface features, like relaxed craters, suggest a degree of plasticity in Ceres' outer layers. While it's unclear whether Ceres hosts a global subsurface ocean or localized reservoirs of liquid water, the mere possibility places it in the company of other intriguing ocean worlds in our solar system, such as Jupiter's moon Europa and Saturn's moon Enceladus. However, there are key differences. Unlike Europa and Enceladus, which are heated by tidal forces from their massive parent planets, Ceres must rely on internal heat sources, possibly radioactive decay or chemical reactions, to maintain liquid water. The potential presence of subsurface water has significant implications for Ceres' habitability potential. Liquid water is considered essential for life as we know it, and the combination of water, organic compounds, which have been detected on Ceres, and energy sources could potentially provide the basic ingredients for simple life forms. While we shouldn't jump to conclusions about the presence of life on Ceres, these findings certainly make it a prime target for future exploration in our search for potentially habitable environments in the solar system. If the idea of hidden oceans and ice volcanoes on a world so close to us has just blown your mind, don't forget to hit that like button. And make sure you're subscribed to our channel for more incredible explorations of our solar system. Trust me, you won't want to miss what's coming next as we continue to unravel the mysteries of the cosmos. Ceres, the largest object in the asteroid belt, has a composition that sets it apart from its rocky neighbors and continues to intrigue scientists. Its unique makeup provides crucial insights into the formation and evolution of our solar system. One of the most striking aspects of Ceres' composition is its high water content. Scientists estimate that up to 25% of Ceres' mass could be water, primarily in the form of ice. This is an astonishing amount for a body in the asteroid belt, making Ceres more similar in some ways to the icy moons of the outer solar system than to its neighboring asteroids. The distribution of this water is thought to vary throughout Ceres. The uppermost layer is likely a dusty, dry crust. Beneath the crust, a mantle rich in water ice is believed to exist. The central region might contain a rocky core, possibly hydrated. This water-rich composition has led to speculation that Ceres might have formed farther out in the solar system, where temperatures were cooler, and then migrated inward to its current position. Another fascinating aspect of Ceres' composition is the presence of organic compounds. The Dawn mission detected these carbon-based molecules, which are considered the basic building blocks for life as we know it. Specifically, the spacecraft found evidence of aliphatic organic molecules, which are carbon and hydrogen chains. The presence of these organics is significant for several reasons. It suggests complex chemical processes occurring on or within Ceres. It provides insights into the distribution of organic compounds in the early solar system. It raises intriguing questions about the potential for prebiotic chemistry on Ceres. In addition to water and organics, Ceres' surface has shown evidence of various minerals, including sodium carbonate, which is typically formed in liquid water environments. Clay-like minerals that suggest past or ongoing aqueous alteration, suggesting a possible origin in the colder outer solar system. The unique composition of Ceres paints a picture of a complex, evolving world. Its current state is likely the result of a long history of geological and chemical processes, possibly including initial formation in a colder region of the solar system, migration to its current position in the asteroid belt, internal heating, possibly from radioactive decay or chemical reactions, cryovolcanic activity bringing subsurface materials to the surface. Understanding Ceres' composition and how it came to be this way is not just about understanding one dwarf planet. It provides crucial insights into the distribution of water and organic compounds in the early solar system, the processes of planetary migration, and the potential for complex chemistry beyond Earth. The unique characteristics of Ceres have led scientists to consider it as a potential natural laboratory for studying prebiotic chemistry, the complex chemical processes that may lead to the origin of life. This possibility makes Ceres an invaluable target in our quest to understand how life might arise in the universe. Several factors make Ceres intriguing from an astrobiological perspective. Liquid water is considered essential for life as we know it. While Ceres' surface is too cold for liquid water, the potential subsurface ocean or brine reservoirs could provide a suitable environment. The detection of organic molecules on Ceres provides the basic chemical building blocks necessary for life. Internal heat from radioactive decay or chemical reactions could provide the energy necessary to drive complex chemical reactions. Unlike the violent, constantly changing surface of Earth, Ceres' subsurface could provide a stable environment for chemical evolution over billions of years. When comparing Ceres to early Earth, some interesting parallels emerge. Like the primordial Earth, Ceres has significant water resources. Early Earth and Ceres both had the presence of organic molecules. Both bodies experience geological processes that could cycle materials and energy. However, there are also crucial differences. Ceres is much smaller, with weaker gravity, affecting its ability to retain an atmosphere. Ceres is much colder than early Earth, slowing down chemical reactions. Ceres lacks a protective magnetic field, exposing its surface to more radiation. Given these conditions, could microbial life exist on Ceres? While it's an exciting possibility, it remains highly speculative. Any potential life on Ceres would likely be very different from life on Earth, adapted to a cold, high-pressure, low-gravity environment. Possible scenarios for life on Ceres might include chemosynthetic microorganisms living in subsurface brine pockets, deriving energy from chemical gradients rather than sunlight. Extremophiles adapted to high salt concentrations and near-freezing temperatures. Dormant microbial spores, possibly deposited by impacts and preserved in Ceres' icy crust. It's important to note that while these scenarios are possible, we currently have no evidence of life on Ceres. The dwarf planet's real value lies in its potential to inform us about prebiotic chemistry and the conditions necessary for life to arise. Studying Ceres can help us understand how organic compounds behave in water-rich, icy environments, the potential for complex chemistry in subsurface oceans, the distribution and evolution of the ingredients for life in our solar system. As we continue to explore Ceres and other similar bodies, we edge closer to answering one of humanity's most profound questions. Are we alone in the universe? While Ceres may not harbor life itself, it could hold crucial clues to how life begins, making it an invaluable target for future exploration and study. The Dawn mission's groundbreaking discoveries have ignited scientific curiosity and opened up new avenues for future exploration of Ceres. As our understanding of this fascinating dwarf planet grows, so does our desire to unravel its remaining mysteries. Proposed future missions. One of the most exciting proposals is a mission to land on Ceres' surface. This would allow for direct analysis of Ceres' composition and potentially sample any subsurface materials that might be extruded onto the surface. An even more ambitious proposal involves returning samples from Ceres to Earth. This would allow for detailed laboratory analysis of Ceres' materials, potentially revealing its full chemical makeup and geological history. Given the intriguing possibility of cryovolcanic activity on Ceres, a specialized mission to study features like Ahuna Mons up close could provide invaluable insights into these processes. Advanced technology could potentially allow for a mission to probe Ceres' suspected subsurface ocean, similar to proposed missions to Europa or Enceladus. Technological and scientific challenges. Landing on Ceres. The low gravity and potentially unstable surface present challenges for landing and maintaining stability. Cryogenic sample preservation. Returning samples from Ceres would require maintaining extremely low temperatures to preserve volatile compounds. Any long-term mission would need to account for the high radiation environment of the asteroid belt. The distance from the Sun makes solar power less efficient, potentially requiring alternative power sources like radioisotope thermoelectric generators. The distance to Ceres results in significant communication delays, requiring a high degree of spacecraft autonomy. Ceres' role in future human solar system exploration. Ceres' abundant water ice could serve as a valuable resource for future deep space missions, potentially as a source of drinking water, breathable oxygen, and rocket fuel. Its relatively stable orbit and rich composition make Ceres an attractive location for a permanent scientific outpost in the asteroid belt. Ceres could serve as a stepping stone for human exploration of the outer solar system, providing a base for refueling and resupply. As the largest body in the asteroid belt, Ceres could play a crucial role in future asteroid mining operations. The classification of Ceres as a dwarf planet in 2006 was part of a larger debate about how we define and categorize celestial bodies in our solar system. Explanation of the dwarf planet category. A dwarf planet, as defined by the International Astronomical Union, is a celestial body that orbits the Sun, has enough mass to assume a nearly round shape, has not cleared the neighborhood around its orbit, is not a satellite of another planet. Ceres fits this definition perfectly. It orbits the Sun in the asteroid belt. Its mass is sufficient for its own gravity to pull it into a nearly spherical shape. It shares its orbital neighborhood with many other asteroids. It's not a moon of any other planet. Ongoing debate on planetary classifications. The creation of the dwarf planet category and the reclassification of Pluto have sparked ongoing debates in the scientific community. Some argue that the current definition is too restrictive and that dwarf planets should be considered a subcategory of planets. Others propose that the ability to generate a magnetic field or sustain geological activity should be considered in planetary classification. There's also discussion about whether the requirement to clear the orbital neighborhood is a useful criterion, given that even some recognized planets, like Earth, haven't completely cleared their orbits. Ceres challenges our preconceptions about the diversity of worlds in our solar system. Ceres shows characteristics of both asteroids and icy moons, demonstrating that the boundaries between these categories can be blurry. The evidence of recent or ongoing geological activity on Ceres challenges the notion that small bodies are always geologically dead. Ceres' water-rich composition provides new insights into the distribution of water in the early solar system. The possibility of a subsurface ocean on Ceres expands our understanding of potentially habitable environments in the solar system. Studying Ceres helps us understand how small planets form and evolve, providing a window into the early stages of planetary formation. The story of Ceres and its classification serves as a reminder that our understanding of the solar system is continually evolving. As we explore further and make new discoveries, we may need to revisit and refine our categories and definitions. Ceres, straddling the line between asteroid and planet, ice world and rocky body, serves as a testament to the incredible diversity of worlds in our cosmic neighborhood and the limitations of rigid classification systems in capturing that diversity. As we conclude our journey through the fascinating world of Ceres, it's remarkable to reflect on how this relatively small object, barely 940 kilometers in diameter, has had such a profound impact on our understanding of the cosmos. Ceres, once thought to be a simple rocky body floating in the asteroid belt, has revealed itself to be a complex, dynamic world that challenges our preconceptions and expands our horizons. The story of Ceres is a testament to the power of scientific exploration and the importance of keeping an open mind. It reminds us that in the vast expanse of space, size doesn't always correlate with significance. This dwarf planet, with its mysterious bright spots, potential subsurface ocean, and tantalizing hints of cryovolcanism, has forced us to reconsider our models of planetary formation and evolution. It has expanded our understanding of where we might find the ingredients for life and has blurred the lines between categories we once thought were clearly defined. Ceres stands as a bridge between the inner and outer solar system, between rocky worlds and icy moons, between inert asteroids and geologically active planets. Its study has provided invaluable insights into the distribution of water in our cosmic neighborhood, the potential for geological activity on small bodies, and the complex chemistry that can occur far from the warmth of the sun. As we look to the future, we can't help but wonder, what other surprises await us in the depths of space? If a world like Ceres, hidden in plain sight for centuries, can hold so many secrets, what might we discover as we push the boundaries of exploration further? Perhaps there are other Ceres-like worlds waiting to be found, each with its own unique story to tell. Maybe the next great discovery is hiding in the Kuiper Belt, or in the atmosphere of a distant exoplanet. The possibilities are as vast as the universe itself. So let us take a moment to marvel at how much we've learned, and how much there is still to discover. Let Ceres serve as an inspiration, a reminder that the universe is full of wonders, and that every new piece of knowledge opens up new questions to explore. As we continue our cosmic journey, let's carry with us the lessons of Ceres. That appearances can be deceiving, that small doesn't mean simple, and that the universe is often more complex and more fascinating than we could ever imagine. If this video has made you see Ceres in a new light, don't forget to hit that like button and subscribe to the Exploring the Universe channel. Your support helps us continue creating content that unravels the mysteries of the cosmos. But don't stop there. Share this video with your friends and family. Spread the wonder of space exploration and ignite curiosity in others. Who knows? You might inspire the next great planetary scientist or astronaut. Remember, every like, share, and subscription brings us one step closer to understanding our place in the universe. Together, we'll continue to explore the wonders beyond Earth, one planet at a time. And keep your eyes on the stars because our next video might just be about your favorite celestial body. Whether it's the stormy atmosphere of Jupiter, the enigmatic rings of Saturn, or the icy plains of Pluto, we're here to take you on a journey through the cosmos. So, are you ready to continue exploring the universe with us? Hit that subscribe button, turn on notifications, and get ready for your next cosmic adventure. The wonders of space are waiting, and we can't wait to explore them with you.